everyone, and thanks for coming. So I have done slides, which I know are a little bit irritating, but kind of a lot of the stuff I'm going to be talking about sort of doesn't really exist in the literature. I wanted to add lots of references so that you can at least some of the basic things. And so some of the reason a lot of it doesn't really exist in the literature. I mean, the first talk is okay, but the third talk, it's because I'm very slow, right? Anyway, so you can find all of these. I'll be putting them up every day on my homepage under talks, so that you have the slides and you can find all the references under that. I figured out how to put bib tech in Beamer, and I feel very accomplished. All right, so right, today we're going to talk about modular and cyclic operands. So the basic idea of this series is that we're going to introduce sort of cyclic and modular operands, a sequel model for cyclic and modular infinity operands, and construct an example with an explicit example of an infinity modular operand who sort of locally models Vattel's homotopy types of modular space, GHG curves with n-marked points. And talk 3 will then be sort of an overview, a little bit of a lot of the history of math. The other reason you want a bunch of references is because I can't tell you all of math, but I can give you a great survey article links. So we're talking about sort of what Grothendieck-Teichmüller theory is, or Lego-Teichmüller theory, and give you an operatic approach to constructing some of these things. And then in talk 4, lots of variations on the Grothendieck-Teichmüller groups and many, many open problems. So see where we go. All right. So it'll be a lot of information, but hopefully I'll give you enough references. Okay. So just get started. I want this to fit. Sorry about the weird scrolling thing. This is so I can scribble. All right, so just we all agreed on notation. I write sigma n for the symmetric group on n letters, and sigma n plus for the extended symmetric group. I'll be just talking about modular and cyclic today, in particular modular and cyclic operands in a general closed symmetric colloidal category. In practice, most of what I talk about in particular tomorrow only works when it's a Cartesian colloidal category. So simplicial sets, which I just call spaces, because it's that habit, or groupoids. So we use the regular Cartesian product there. And we're going to be doing completions of these categories as well, or pro objects in these various categories. But they're all Cartesian colloidal closed, and in general, I just write HOM for the regular internal HOM. All of the examples I just put up there are simplicial, meaning they're tensored and co-tensored over simplicial sets. So that's math. And then hopefully I remember to always put the R when we're using the homotopy mapping space. Right. This actually gets pretty important later for some of these things are not true if I use the wrong mapping space. So if you're confused at any time of that, let me know. All right. So I'm going to start by saying that, so we're going to introduce operads as kind of a generalization of categories where your morphisms have many inputs and one output. Modular and cyclic operands somehow to me don't feel categorical. In fact, as you'll see with cyclic operands later today, it's not really clear what the right definition for colored cyclic operands should be. There are many ways you could interpret them as a generalization of categories. They are very geometric, however, so like these sort of colored definitions or multi-sorted definitions look a bit funny. So in particular, I'm going to make a choice, and I'm going to pick C to be a set of colors or objects, which comes with an involution. So I really want to have a map from C to C, where if I apply it twice, I get the identity. So I'm going to use the dual symbol for reasons that will make sense later. But so C double dual is strictly equal to C. I'm going to probably try to avoid the language, but I'll say profile. I just need a list, just a finite list of objects. So, and I would denote it with an underline. So just arbitrary elements of C. I have a student at home that really gets irritated with me that I enumerate finite sets. You can do this entirely coordinate free if you'd like. I have references for that, but it's useful for our purposes. And anyway, and then we'll talk about like permuted profiles where we sort of permute the index there, right? So I am going to have my finite sets. I'll write an enumerated list. And I'm going to be able to permute them. And for any two profiles or just lists, I want to write a composite where I basically place the dth entry of D, sorry, the jth entry of D into the ith entry of C. But I'm going to do this in a really particular way. I'm going to cyclically permute so that J comes to the beginning and takes the place of D sub 0. And then I'm going to compose into the ith position. So you have this list where I've cyclically permuted the list so that DJ was the first entry in the list. Then I compose it in the ith position of C. And I'm only going to allow this to be true. I can only compose when, in fact, DJ dual is equal to C. So I want the involution to be guiding when I can compose things. And we'll see some topological examples of why this is a good idea, and maybe some categorical ones as well. Okay, so what is a colored modular opera? So I'm going to say that a C-colored genus-braided sequence in my base category E, so spaces or groupoids, something like this. It's going to be a collection. I'm going to have two indices. So I'm going to have a collection of objects in E, where I index by G, the genus, and where I allow the second component runs over all profiles in my color set. So if I just had, if C was a single point set, if it was a one colored object, then I would have a bi-graded sequence. It would be in G and in N. And I'm going to have a write action where I can permute the profile, but the genus is always the same. And of course, maps of these things are what they have to be. They're going to be, it's just sequences of objects, it's just massive graded objects in space, right? But I want the genus part to sort of always be fixed. Oh, and I forgot to actually turn on my time so that I don't just talk forever. Which when I ran through these with my students before, went on very, very long. Be happy with some the abbreviated version. All right, so a C-colored modular opera in my base category E. This is going to be a genus-graded sequence together with two types of operations. So I'm going to have a composition where I can glue things together, or you should think about this as a little bit like function composition. So I have where I'm gluing profiles. This is if I cyclically permute the entries in D, the J's position being in the front, then I compose it into the ith position in my sequence C. And the genus adds. And of course, this is only going to be defined if DJ dual is CI. Similarly, well, not similarly, kind of a new operation, what's sort of different than Operads, is I have a contraction operation. So basically, we're going to be drawing this in terms of graphs. So I can think about another reason for slides is I don't draw very well. So if I think of like one operation, Q, this is sort of a P, I, J, Q. I glue some tree, but now I don't really have an input or output. So I just have a little spider. And I glue its I flag to the J flag of my other little spider. And that's this type of composition. And a contraction operation is where I start with something that looks like a tree, and then I glue two legs together. Right, so I have sort of contraction operation. So I'm going to have operations that look like trees, right? So like Runa was writing them this way, so they look kind of categorical, but I don't have that output arrow. They just sort of, anything can be an output. That's why I have this sort of cyclic permutation. And I also can glue operations to themselves. You can think about this as basically if you have, if you're looking at tensor products of vector spaces and you have like the dual. So if I had them, maybe the instinct to have would be if I had V tensor, V tensor, V dual, well, you would contract that to V. Okay, because V tensor, V dual, V tensor. So I'm thinking of that kind of thing. A contraction essentially kills an operation in its V. And these satisfy a series of axioms. So basically, I want both of these things to be associative, strictly, unital, sometimes, and equivariant, so that I can commute all of the labels. And I've given you a few lists of where you can find these. So somehow it gets smaller anyway. All right, so a map of modular operads is going to be this map of sequences in E that can be with that. So as I was saying, one reason for all the examples is this is a blend of a couple of different definitions you'll find in the literature. So in the one colored case, you often see genus graded modular operads. So I've given a link to a paper by Hinich and Weintraub, which also has all the axioms for associativity, equivariance, and unitality in the genus graded case. The original definition is actually due to Getzler and Operads in 95, but they required that they have a stability condition. So it was a set of graded operations such that everything vanishes unless 2g plus n was greater than 0. And this was designed to sort of model the gluing together of genus G curves, stable genus G curves, hence the word stable, in the moduli space. So the idea was that you could glue together curves as long as they were stable. Okay, watch that later. Now, if you forget the genus grading part, which I need because I'll be working with a lot of operations, truncation operations with modular operads, which you need the genus grading to do. Then you see C-colored modular operads, so colored modular operads that were in a paper I wrote with Phil Hackney and Yau, sort of where we introduced a Siebel model for infinity modular operads, or in a very nice paper by Sophie Renier, or I guess I should also say in a paper of Jokins with André Jovel. They're called something like compact. No, I forgot. Compact
symmetric multi-categories.
Compact symmetric multi-categories is Jokins for these things, and Sophie's as well, or colored modular operads. So without the genus grading, some things simplify, some things don't, but this sort of a thing. So, but this is what we need for our geometric constructions we'll be doing today. Okay, so I'm going to spend a while talking about. So the main part of this series is actually an explicit example. So if you've not seen modular operads, you will, well, you make good life choices, and you will see one very, very explicit example over a couple of talks. But one thing that we'll need to think about is how do you generate a modular operad from a graph? So I need to tell you what I mean by graph. And this is going to feel like a very belabored definition, but you'll see where we go with this, right? So I'm just going to say that a graph is a diagram of finite sets. Okay, so I'm going to have, I can even make this a little hook there. So H is going to be a set of half edges. And I is an involution that glues one half edge to another edge. So this sort of allows me to assemble edges out of pieces. V is a set of vertices. D is some subset of the half edges, which I'm going to glue to V, to a vertex, via a partial function T. Okay? So I'm just giving you a series of sets, and we're going to do a bunch of examples, and they're gluing data. Right? So I'm thinking of a graph as a purely combinatorial object. So an edge, what we would normally draw as an edge, is an orbit of the involution. So, and I will occasionally actually write it as E is A times A dual. And I'm using the dual notation so that it agrees with the moduli space, or sorry, the modular Operad notation that I've used before. The set of half edges which are glued to a vertex, which are around a vertex, well, we're going to call that the neighborhood of V, but that's just the inverse image. And so if V is some vertex in there, then T inverse of V tells me which half edges are glued to it. Yeah. And then all the half edges which are not glued to a vertex, called the boundary. So they're the outside edges. So to make sense of this definition, let's actually look at some examples. Oh, good. Okay, so here's just a floating edge, right? So I want to just look at this graph as an actual, and I want to write it down combinatorially. So what is this object? So I have two half edges, A and A dual. I have the involution I, which takes A to A dual, and therefore glues them together to an edge. Well, there's no vertex, so I just have the empty sets here. Okay? So I can have an empty set of vertices, I can just have a line that floats around. I can have a bunch of lines. I haven't said things are connected yet, but we won't. Okay. So everything in this is a boundary. So both A and A dual are in the boundary. So this is sometimes called eta in the dendroidal sets language. So I'll use the same notation. So eta for the half edge. And its boundary is the set A and A dual. So these are the things that we would think about. And later in our talk, we'll be thinking about embedding this into a surface. I really can't draw. And so the graph is here, and what are the boundary points correspond to boundary components will be the way to think of the notation. So here's now A dual, and here's A. Okay. So this will be an important object later. So here's another example, which is just a corolla. Okay, so this is a graph with one vertex. So I have V is my vertex set. I've got 2 times 4, 8 half edges, which I realize I should have written down first, because it'll end up taking all the space. Right. And well, the subset that's attached to the vertex, this is the A1, A2, A3, and A4. So the neighborhood of my vertex are these half edges. Right? So this is the part that's close around to the vertex. And the boundary are their groups. And the edges are the orbits, or a dual or making an edge. And one advantage to this, what we're going to be doing later, is I'm going to be actually changing the labels. So I'm going to want to embed this into a surface. The boundaries are going to go to boundary components, but I want to sort of cyclically move the internal parts, right, to to get some geometric information. So you actually want this type of combinatorial structure so that you can change the labels around the neighborhood and keep the boundary fixed. It looks cooler when you draw a surface. All right. But this is a corolla with four legs. Our boundary has 4 components. Okay, and another example are things with internal edges. Okay, so this contracted corolla will be one of my generating pieces of the graphical category that we'll be talking about soon. And what do we have here? So I have 2 edges made of, oops. We'll call this A1 dual. I think that's a 0. 0 dual. Okay. And then we have 1 vertex. And the subset of objects, got my little involution there, that are attached to the vertex. Well, that's going to be A1, A0, A2, and A2 dual. Okay. So the neighborhood of the vertex is actually all of these pieces. And the boundary are the 2 half edges that are not in the domain. Right, so the boundary of this graph is then A1 dual, A0 dual. And the internal edge here, right, this is sort of given by the orbit. So I can call this guy E, is A2 dual. So it doesn't take too long to get used to this formalism, although it does feel like a lot of work for writing down the graph. But it turns out to be less work. Well, actually, I'm even going to put more work into it so that I can simplify some constructions later. But this gives you a lot of control over how we work with graphs this way. Okay, so in fact, I want every graph to come with extra structure. So a lot of this is some of this is overkill, and this is not the way we did it in the paper, but it's very useful for defining the topological stuff that we'll be doing later. So you have on the one hand, you have to carry around a bunch of information, and on the other hand, you get a bunch of information. All right, so let's look at this. So I'm going to enumerate all my vertices. So if I write down vertex 1, that has a meaning, and I'm going to carry that label around. And you might think that seems kind of silly, but here's an example where this might make a big difference. Okay, so this guy will really mess with your life. Certainly cost me a couple of years. So if we don't enumerate the vertices, then we can't really talk about how this can be decomposed into component pieces, for example. All right, I'm going to give a labeling of the half edges around each vertex. So going back here, like these around the vertex around the neighborhood will have a number, and I will actually mean it, like that has a number, and carry it around. And similarly, I'm going to label the boundaries of the graph. Now I can permute those labels by just, composing with elements with bijections, right, with the symmetric groups. But if I write down something is that number, then I really mean it. Okay. And that has some great advantages, which we will see tomorrow. Okay. I'll usually just sort of suppress the information unless we're using it, but all of this is here in the graphs. So I will also make my graphs genus graded. So we're going to have to work in genus truncations of modular operads. So I want to restrict to say modular or contraction operations, but I only want genus 1, genus 2. In order to do that, I need to actually know what that means, to have a go over that on the graph. So I'm just going to actually give this additional function, and I'm going to label each vertex. So it has a number, and I'm going to give it a genus. Okay. Then the total genus of the graph is going to be by this formula, which I should have set off, which is, so I'm going to add up the genuses on each genuses of each vertex, and then add the first Betty number of G. And so I'm going to show you an example right here. All right, so here's the graph, and I've labeled this vertex as, so I guess we'll call this G of V1, I decided was 2. G of V2, I decided was 0. So if I look at the genus of the whole graph, which I guess for little g of G, which is just bad. So G of V1 plus G of V2 plus the first Betty number of G. So this becomes 2 plus 0 plus 1. Okay, so the whole genus of that graph is 3. I didn't say why it makes sense to take the Betty number, but you can geometrically realize these combinatorial graphs. And therefore, it's not complete nonsense. Okay, so my graphs are carrying around a lot of data. So each edge has 2 pieces. Each vertex has a name. The neighborhood around it is labeled, and the boundary parts are labeled. And the vertex also has a genus. So these are our special graphs. All right, so now I say that, well, given that information, I can actually define a modular operads. So if I take some graph, I can generate an each colored genus graded sequence, which I call like this little bracket G. Right, so here, what am I going to take? So maybe I'll draw a picture. So I'm going to say that entries of this sequence in sets is just a set-based thing. It's going to be the single vertex V if the genus of V is H, and the profile here is actually equal to the dual of the neighborhood. Right? So I'm thinking about like this as an operation. So here's V, and here's C1, C0, 2, 3. Oops. I guess we'll make these duals. Okay, so here, this would be, this would correspond to a single point V living in G of genus 0 with profile C0, C1, C2. So since I didn't put any genus information on C, and for each vertex of my graph, I'm going to write down the corresponding part sequence. All right, then what I'm going to do is say, I can take the free modular opera then generate it on this thing. I have I can just freely add or contract anything that can be glued together. And what does this actually look like? So I think that the point is why are these graphs, why do I have the duals in my definition of the modular opera, and why are the duals in my definition of the graph? Is because, for example, the composition operation is going to be witnessed by some internal edge of a graph. If and only if I've glued together Ci and Dj to make that edge. So, for example, right. So this internal edge here, which is equal to basically being telling me. So if I have these 2 elements in my neighborhood, this internal edge means that the involution takes Dj to Ci, so, or vice versa. they're dual. So that's the way the edge comes into being, right, in this combinatorial language. And I'm saying that this is actually basically a composition of these two operations, this one. So it's designed to have that. And there are no other compositions. I'm not going to just sort of have things that exist that I didn't see before. Okay. Similarly, contractions, it's the same slide, but with it. This is only going to be witnessed by an internal edge that looks like one of these loops. So here, right, I only have a contraction operation in this free modular operad if, well, that was weird. Right, if Ci and Cj can glue together to become an edge, and that means it's Ci equals Cj. There's formalism. Okay, so it sort of feels a little like I'm moving it up to fit, but that's actually true. That is not perfect. So this was designed, I mean, the definition was designed to fit the language. Okay, and what we'll be thinking about as we try to infinity things, what we're going to be doing is thinking about what it means to witness this composition, and sort of instead of make it associative, it will be associative up to him. Right. The goal. All right, so let's do, I had this as an exercise. Maybe I'm going quite fast, so I will tell you, maybe I'll get you started. So here I drew a graph. Like I said, this is online for you, and I didn't label anything, but you can see that I have the little zeros these are genus 0 vertices, and then I give you one genus 1 vertex. So here, for example, let's see. So here I have a generating operation of my free modular operad for this graph, which is going to live in, I guess we'll give this a name, A1, A2, A0. So I have some single point, which I'll call V, which lives in the space G of genus 1 with profile A2. Right. And there will be some compositions with whatever happens up here, right? Or contractions. And you'll have to check that one of these is, you can compose and then contract, or contract and then compose, but you'll still get the same.
The profile will be with duals or
no? So yeah, so the duals are, it's almost like, so the neighborhood is, yeah, I should write the duals. That's right, here.
Okay.
And then I want to left. Yeah, thanks. Good point. Right. So these are some generating operations, and it's worth playing with. Right. The easiest thing to do is just, if you haven't seen this before, is just use a tree and generate an operad from it. That actually works the way you expect it to. And then you don't have to deal with duals, and then this sort of is the progression. So what are some other examples? So like I said, in some sense, these things are not really categorical in the same way. So one example of modular operads are compact closed categories. So these are symmetric modal categories in which every object has a dual. And we have some morphisms, right? So evaluation and co-evaluation maps. And they satisfy these snake identities, which I'll just draw like this. So for evaluation and co-evaluation. So this is an example of a colored modular operad, right? So every object has a dual. This is the equivalent of sort of how we're going to have the categories are like truncated versions of operads, right? Where all the higher arity operations disappear. So you have, this is first, so you have this idea, you have like the category of all small categories sits inside the category of colored operads that Mercer is describing. Okay, just by forgetting any higher arity operations. The analog for these colored modular operads, as far as I know, compact closed categories. This is an example in this paper by Sophie Rainier, and I don't know if it's explicitly spelled out, but it's kind of implied in the paper by Joachim and Joel.
He was more like the symmetrical model categories as Operads. So you're taking all of the operations like.
Oh yeah, I guess it's sort of. Yeah, I guess it's more like the. Yeah, sorry, that's not quite the right thing. Thank you, Ren. And also, so it's not that, it's so every operad generates a symmetric modal category. So you have. Did that right today. You had the other way. That's you can go both ways. So it's like that, sorry. The underlying oh, I didn't do the underlying categorical thing for this. I did for cyclic operads, so we'll get that. So these are kind of so there is a sense of duality that happens, and I mean that in also the categorical sense, but it's quite strict. It's modular operads. Okay. So I will correct this. All right, that's my correction. All right, so what we're going to play with a lot is that the genus of the operations, we can kill off some of the higher genus things. And so some things work better in genus 0, when we talk about surfaces, lots of things work better in genus 0 in that case. And sometimes we need things that work in genus 1 on elliptic curves. So the genus K truncation of a modular operad is just a quotient set, right? So in the category. And where I'm going to say P less than or equal to K is the quotient of the original modular operad P by P greater than or equal to K. So this is the sub-object generated by all operations, so all compositions or contractions, which lie in some element of my graded space, of my graded sequence, with the genus greater than or equal to K plus 1. So it's somewhat what you would imagine it being. You just you trivialize any operation with genus higher than G, higher than K. There are other ways you can play around with truncation. So one of the references I gave here, they truncate by a different dimension. Maybe I won't mention it, but this is what I mean by genus K truncation. So what you'll often see in the literature, so this is that a cyclic operad is the genus 0 version of a genus 0 truncation of a modular operad. So a C-colored cyclic operad for us is going to be a genus 0 truncated modular operad. So what gets killed when I kill off all the higher genus operations, all the contractions disappear, right? So we don't have any of these genus 1 graphs. This dies, right? And all my vertices will have genus 0 as well. So I'll just now have simply connected graphs, trees, unrooted trees will be sort of the graphs living in cyclic operads. All right. So what does this consist of? And I'll drop the genus then. This is going to be right, graded, just a family of objects indexed by every profile in C, together with these type of cyclic operations, these casing profiles, whenever Ci equals Dj. Okay. Now, I will say that without the genus grading, I don't really know how to prove this. It's often said just in general for graphs, but I don't really know how to do it. But let me just give you some properties of truncation. So in fact, in any of these ones, I can define a functor now from modular operads in general down to like G truncated, sorry, killed off operations for any G or K. And this has both a left and a right adjoint. And where does this actually come from? Well, if you wanted to build these functors from scratch, certainly the way I would do it is that you find an operad whose algebras are modular operads. And so operations of that are genus graded graphs we've just been talking about. And then I throw out the other ones. So I have, let's just say I have an operad for the whose graphs are all genus graded graphs for with genus greater than less than genus less than some chosen G. This is obviously a sub-operad of just a general category of graphs or graphs. And then I have junctions. When I have a map of operads like this, I have adjunctions of their algebras. Right. So if I have an inclusion of this operad, I have a sort of extension restriction of scalars type of thing that happens on their algebras. And this is how basically what truncation is. So I'm including the graphs into the graphs where I have all genus, and then I'm doing some adjunctions on their algebras. This sort of thing you can find in an appendix. I think I put it here. There's an appendix A of this paper by Gabriel Drummer-Cole and Phil Hackney from 2019 that has a version of this for one colored. Or it's proved in a more constructive way in this paper. Was 4 authors, and I can't really properly pronounce any of the 4, so I'll just say and what's really useful, and so when we were playing with these things a little, if you've ever thought about cyclic or modular operads, so if I take G to be 0, so I forget from modular operads, I kill all the higher genus information down to cyclic operads. That left adjoint is something that's called the modular envelope, which is a particularly nasty thing. It freely adds all higher genus operations. And the right adjoint is a little bit, it's also kind of a slew type of construction, or it's more of an inclusion. But they both behave reasonably well and are fully faithful. So I will be playing with this a bit. And in particular, we can sort of, go from the cyclic operads up to modular operads and forget back down, and we're still in cyclic operads. We end up in the identity. So one of the things that's a goal for us is we're going to build this modular operad out of, say, moduli spaces. Genus 0 ones behave reasonably well. So I'm going to do some calculations there, move it upstairs into all genus moduli spaces. And then I have no idea what's happening, so we're going to forget back down. Right. And we're going to play this push-pull game in order to actually talk about higher genus operations. They look harmless with little loops on the graph, but if you think about them as topological spaces, things get unpleasant. All right, so now another categorical thing. So what is a cyclic operad? So one example, and this is closer to thing Runish was talking about either, the symmetric familial category generated by an operad, is star autonomous categories. I don't know where the name comes from, but it's such as the name. So this is a symmetric familial closed category, which has some global dualizing object. So an example would be vector spaces, or finite dimensional vector spaces, and the global dualizing object would be the field. Because maps from Hom, say, as Hom V K C dual. So it's like a global dualizing object. If you have a star autonomous category, one of the properties is that a double dual is isomorphic to A. So if you, for all A in my category C, if I take this isomorphism to be strict, if it's the identity, so if A double dual is equal to A, then I can define a colored operad C, where that's fancy Q. So that's Q, where the profile, so Q from A0 to A1 to AN is basically the maps from A0 into now the tensor product of A1 AN. Okay. This is fully worked out in this example of this paper by Phil and Gabriel Drummond-Cole. Now, I do not know if it's still true if you just take the isomorphism. I don't think so.
Do you want to maybe put a star on one of the A0s so that
I do.
awesome.
Oh, that's not the one I want.
Thank you.
Yeah, I can choose. I guess we like that one. Now I really want to put on the other one, but anyway, it's symmetric. So you get an equality here. I don't know if this is true in general. I haven't been able to prove it like this. So if somebody knows that, I'll be very happy. Yeah. But it's certainly true if we have a strict duality. Okay, and I should say, while I'm constructing these like symmetric polynomial categories out of my modular cyclic operads, this is not quite the same thing as like taking the envelope of a cyclic or modular operad. That's what you'll see some of that either on Friday from me or from Ken, depending on which of us get to. So this is what the sort of symmetric polynomial category underlying this type of cyclic operad is. We also have okay, now this is the example I actually wanted, but for modular operads. So I have analogous now to the idea that cat sits inside operad. The objects that are sitting inside cyclic operads in this definition are called anti-involutive categories. I also don't know who came up with that. Well, I guess star autonomous is probably bar, but I don't know where anti-involutive arose. But what is an anti-involutive category? So this is a category C, together with the functor from C op to C, such that if I do it twice, I get back to the identity. This is giving me basically an involution on objects and morphisms. So any anti-involutive category with objects at C, you can define a C-colored cyclic operad where I take the maps from C0 to C1 are the morphisms in my anti-involutive category C from C1 to basically C0 dual. Kind of how I'm thinking about that, right? And it's empty otherwise. So this is just an inclusion of anti-involutive. This is the analogous thing from anti-involutive cat. I'm not sure what the usual notation is for that into cyclic operads. Okay. This is the analog of categories sitting inside operads. So these are kind of strange objects. And what I want to point out is that it is also a choice that we've made. So it's not really clear what the ideal definition of a colored cyclic operad should be. So if you do not have the involution on color sets, then instead of anti-involutive categories, sort of is a categorical part from there, what you actually have is dagger categories. So you could do this whole thing with colored cyclic operads, and then you have basically dagger cat sitting inside sig. And I'll tell you the reason that we decided that we don't like that is because the homotopy theory of dagger categories is a deeply unpleasant experience. So at least for me, I know there are people working on it, and so it's not really clear that this is what we want. Certainly for what I was interested when we were coming up with the definition was one colored cyclic operads, and then the involution vanishes. So it doesn't really play a role, but this is actually kind of an interesting question. So if you have infinity cyclic operads, I suppose without the involution, they should restrict to some infinity dagger category, which I don't know what that is, but I'm aware that some people are thinking about. The definition we've chosen of a colored cyclic operad closely resembles that of a cyclic multi-category. So this is in a paper by Eugenia Chang, Nick Gursky, and Emily Reel from 2014. In fact, so what they call a cyclic multi-category is just a non-symmetric colored cyclic operad. So that means I forget all the symmetries, but I do keep the cyclic action. And otherwise, then you get something called a cyclic multi-category. But the other main reason for the involution of color sets is that it makes it much easier to construct functors from cyclic operads to operads and dioperads, things like that. And it makes my graphs look. That's the main thing. So I do want to have this as a point that I don't think this is a settled thing or very clear what's the correct definition. We're making a choice because it's convenient. If someone has an idea of what, and I guess there's a non-symmetric version of the cyclic operads without involution that are related to two Siegel spaces in particular way, which our other speaker can tell you about. So there are variations on these things that we can play with. So both a disclaimer of that I'm not giving you the authoritative definition, and there's a lot of work that could be done in this direction if you're looking for things to play with. But the main thing that we like about this is that it makes sense to talk about maps here from cyclic operads to operads, which actually emit both left and right adjoints. And we can do this all in the same graphical formula. So, because we're going to be infinitying this, and I'm going to use those graphs to infinity things. So when I want to do that, I want to think about, cyclic operads are actually operads plus something called a cyclic structure. So to give you now to simplify considerably, you just go to classical one-colored operads in my base category E. I'm going to write Zn+1 for the cyclic permutation that basically generates the sort of cyclic action in this extended symmetric group. Okay. So now I'm just giving me my rotation of my labels. So if I define a cyclic structure on regular operad O to be some kind of, oops, that's supposed to be the plus, but anyway, the extended symmetric group action on my ON. So I'm extending the regular sigma n action to a sigma n+1 action on my n-area operations. And I want that to satisfy some conditions. So if I live in just the regular symmetric group in the subgroup, then I just want the operad action. And if not, I want to have sort of rules that say, well, if I cyclically permute x circ I with y, so this composition where I've glued x to the ith leaf, so this is y, this is x. If I now permute, if I act on this label, so I change this output to here, well, that is one of several things depending on what I is. So it's either, well, I cyclically permuted x first, and then I composed y in the ith plus first piece, which you can kind of see from the picture I drew there. And if I was composing in the last entry, sorry, in the first entry, then I actually just swap the order of composition and act on both. And I've given you a couple of exercises, which if you haven't done, if you haven't played with these, are extremely useful to do, because you just write down some trees and calculate permutations, which is not something I like to do in public, but I can sit down and do with you if we're not being recorded. It's amazing how hard group theory can be when you're being watched. So and you can actually then deduce other operations. So I didn't mention the case when I equals 1 and m equals 0. If you want to deduce that, you sort of have to work this out. Or you can just see that actually all of the cyclic operations, so x, I, circ, j's, can be obtained via Operad maps by acting some way or another. So what this is saying is that, well, actually, let's say that this is my x, and then I wanted to do compose with y. Well, so this means that I'm going to glue the leaf. Sorry, there shouldn't be arrows on these things. I'm going to glue the boundary component labeled 2 to the boundary component labeled 1. Right, so what does this look like? Oops. So now I have 2 and radiating out in the right direction, hopefully. Well, this is 0. This would become 1. You obviously have to re-index, but I'm just pointing out. So this is what the gluing means. So means that I glue the boundary component labeled 2 with the boundary component labeled 1, and then I have to relabel all the outside boundary components. So I could figure that out, or I could just change the labels on each of these things in a particular way, and they will all be equal. And this is a really useful thing, because when I have I circ 0, this is Operad composition. This is the regular Operad composition. So I like being able to take whatever version I want and rewrite it. Okay? That way I can be lazy and not have to calculate what happens to the symmetric groups to relabel these things. And this is really worth just drawing a couple of pictures like this and trying a few, and you'll see it works out very easy. So if you haven't played with these things, this is a really useful exercise. It'll take you 20 minutes, and then you'll feel like you understand all of cyclic operads. I mean, you won't, but you will feel like it. I don't understand them either, but it's definitely one of those things. All right. So, like I said, in fact, this cyclic structure is kind of interesting, and the example we're going to see, the main example of our series of talks is a cyclic operad built from surfaces, where I'm doing just exactly this thing. So I'm going to have, gluing. I'm going to take a surface. Inside lives a little graph. This is just going to have some labels on my boundary components. And I'm going to glue this surface to another surface. To make a nice pair of pins. And it's got a little tree living in it. Okay. So I can basically glue any pair of boundaries. It would make sense, right? Topologically, I shouldn't be thinking that I always have to glue the 0th boundary to the, like here. So if I wanted to build an operad out of surfaces, I would always glue the 0th boundary to something that's not 0. I would keep 0 fixed. But that doesn't seem necessary. So the only reason we should deal with 0 is a special boundary. So the idea is we're going to be looking at something like that. Now, how do you actually write it down? That's the trick. And let's say I started with this operad and you wanted to build the cyclic operad where I don't care. Well, you can try a bunch of things. And if you're like me, none of them will work. So you can look at the sort of left and right adjoints of the forgetful functor from cyclic operads to operads. The right adjoint is really great if you haven't seen it. It's kind of interesting. You just add only the cyclic permutation. The left adjoint is that you freely add all of the cyclic permutations. So that's certainly one way. So you have an operad you would like to think about as a cyclic operad, you could just hit it with an F, right? But will it be the right thing is kind of something to play with. So here's an example. I mean, it's one of the nice examples of something that admits a cyclic structure, but it doesn't come from the left or the right. So the framed little disk operad, this is a variation on the little disk operad, which I'm hoping everybody has seen. But so this is the space of configurations of n disjoint disks embedded into a disk, or I do this by either translation or rotation or rescaling, right? So I have a framing. I'm actually choosing a rotation. So I'm basically picking a base point on the disk. Now this thing, well, it's not a cyclic operad. It's an operad, but it emits a cyclic structure. In fact, it can emit probably multiple ones, but there's one that's well known due to bumping. Right, so what you actually do is so what does an element look like in here? So a point in FDN, so I'm going to put a base point on each disk, so I can actually keep track of rotations. So this would be a point in FD2, 2. So 2 little disks embedded into one big disk, right? Now, what I want to do, what does a cyclic action do? Well, it basically takes the outside, which is the 0th boundary, and changes it with one of the others. Well, that doesn't make sense from this point of view, but you can blow it up a little, like so. And then, of course, you can sort of just permute the boundaries, right? You can think about, what does this look like? Well, I mean, it's not exactly the same, but it's the same kind of data of these circles on space. So the cyclic structure of Bundy, it's a really short little paper. It's very nice to read. Basically says you take a configuration and instead you replace a configuration of disks inside of a disk and replace it with a sphere with n+1 holes, right? So this is now a sphere with 3 holes instead of 2 disks inside a disk. Now I can actually, so the boundary disk of the one becomes a boundary component of my surface. So then I can act by just permuting these boundary components, but in order to make sure this is well defined, you actually use the framing specific way, right? So to make sure that this is a well-defined thing, you have to actually keep track of these frames. Right? And then you can just look at this rotation, which basically changes 0 into 1, just rotates. And that actually defines a cyclic structure. You can prove that explicitly. But this is not going to be the left or the right adjoint. There's no sort of trick to doing this. You just have to actually, unfortunately, check that everything works. Or if you're lucky, you can just read this paper, but you checked that everything works. Yes, it's fine. Yes. Well, good. I'm on my last slide. So, okay, and similarly, and one that we will use is then the sort of groupoid model. This is the parenthesized braids. Oh, and I just noticed. Well, I made at least one citation error, but it's to a paper originally, so that's the wrong paper. But anyway, I'll fix that later. So the operatic parenthesis ribbon braids is a group-wide model for frame disks, and this also admits a cyclic structure, but it's one of these. It comes from the one I just showed you, and we'll be playing with that a little bit. So it's sort of unintuitive cyclic structure on braids. Right, I'll stop there. And like I said, there are pages of references on purpose. So sorry about that.
Okay, we have time for one quick question.
It's a very educated mic.
So Natalie here.
Let's go back to this last cyclic action on the frame with this. I mean, you're sort of changing model of the frame with this, right?
Exactly, you change the model. So you what Bundy does explicitly, and sort of the cyclic structure on surfaces that I'll be talking about is sort of what I'm drawing. But what Bundy does is he embeds this into the sphere. Right, so now my boundary disk becomes like the upper part of the sphere. So I take my my disk with my embedded disks, and I now map it into a sphere with some disks in the northern hemisphere. And then he does like stereographic projection down.
So he goes back. So there's the standard model of the frame. There's this. You can map it to surfaces, and then you go back.
And then you go back by projection. Yeah. So the actually what's kind of really pretty is that the cyclic structure on ribbon braids that we saw from Campos, Idrissi, and Wilbacher. Thank you. Somebody has done their homework, and that is not me. Anyway, so is given by looking at configurations in the complex plane, and then the cyclic structure is given by the sort of involution of the complex plane. That turns out to be equivalent to this one, but it comes from kind of a strange place. Like it's not where you would expect it to come. So you could take your ribbon braid operad and do the left and right adjoint or do a bunch of things. You get a cyclic operad. It's weird, but it's like it's somehow not really the same thing that you would want sort of to map down to surfaces. And which I will tell you tomorrow, the reason you want the ribbon braid operad to map to surfaces is because right, the pure ribbon braid group on n strands is the mapping class group. So where like there is a relationship between ribbon braids and surfaces. So you would want the cyclic structure on your sort of operand groupoids to be the same one you're seeing on surfaces, but to make that comes from a very unintuitive place. I will try to make it more intuitive, but to be honest, it also confuses me. I mean, it's the thing that works, but it's sort of, it didn't strike me as particularly obvious.
Okay, so now let's thank Marcy again.